Hey, Mr. Luong. We're doing FRQ number one here. Part A asks for free body diagrams. So I'm gonna just start with the mass on the table real quick. So this has a mass of big M. It's being pulled to the right by the string. So T, the force acting on it is T. Um, Gravity is acting on this object. So F of G, and then also has an F of N since it's resting on the surface and the surface is pushing back on it. And then for the other object, the small one hanging, small m, is being pulled down by F of G, but there's also a tension that's pulling it back up from the string. And then since F of G is is moving downwards, F of G has to be greater than the tension. Alright, moving on to part B now. Um, I know that the acceleration of the hanging block is the same as the acceleration of the whole system, so I can just find the net force on the whole system. So the only force acting on the whole system is F of G, and this is equal to the mass of the small block plus the mass of the big block times the acceleration of the system, because I had to combine the masses since I'm looking at it as a whole. So then F of G is equal to mg since it's the force acting on the small block, and then I can just wait, let me write this out first. I can divide the 2m plus big M over, which gives me a system, but since a system acts on like the whole system at the same time, this is equal to just a hanging. That's the answer. Alright, moving on to part C, I asked to find the tension between the two blocks. So I would say F of G minus T equals MA. Since I'm focusing on the hanging block, F of G, T, and then MA, net force. And then this is equal to, FG is equal to MG minus T equals MA. If I isolate for T, I get T is equal to mg minus ma. I can factor out an m, which gives me T is equal to m times g minus a. That's it. Alright, moving on to part D. Part D asks what happens if the mass of the sliding block m increases, what is the effect on acceleration and tension. So looking at the block on the surface, the forces acting on it is just T is equal to ma. So a is equal to T over m. But if m were to increase, that means that you'd be dividing by a bigger number, so it means a would decrease. But then if I look at the other equation, setting up the equation for the other smaller block, it would just be fg minus t equals small m times a. If I isolate for t, I would get fg minus ma equals t. But then if the acceleration decreases, that means I would be subtracting by a smaller number because I'm multiplying by a smaller number, which means that t should increase. Alright, moving on to part E. Now there's an Fk that has been introduced to the system because there's now mu k, or friction between the surface and the block. And so now I want to find acceleration, so I'm going to look at the whole system as a whole, and the forces acting on it are the force of gravity and the Fk, which is equal to this mass of the both of the masses combined times A of the system. And then F of G is just equal to the small mass times gravity, and then F of K is equal to just the normal force times mu k. This is still equal to just mass plus mass over A cis. So write this again. Put the F of N, since the block on the surface isn't like flying into the air, they had to the F of N has to equal to the F of G, that top block. So it's mg mu k is equal to m plus m times a cis. But then I can factor out a g right here. So it would be g m minus big M mu k. I can divide over this m plus big M, which gives me a of system. There you go. Alright, so moving on to part F, asking us to derive the tension between the two blocks now. Um, so first, I want to set up the net force for the hanging block, and the forces acting on that are just F of G and T, and this is equal to M, small m times A. And I'm going to set up the net force for the big block, so the force acting on that are just T, Fk acts against it, is equal to big M times A. But then, not, since I'm trying to find T without having A in the answer, I'm going to just isolate for A. I'm doing the left equation because it's a little bit easier. So I get F of G minus T over M equals A. And so I'm going to plug that into the other equation. So I get T minus F of K equals big M times F of G minus T over small m. Now I'm going to convert some of these over to their expanded form. So I'll get T minus F of K is just equal to F of N times mu K. This is equal to big M times F of G. F of G of the hanging block is equal to mg minus T over M. But then over here on the left side of this equation, F of N, this is the mass of the big block. So I'll do Fg mu K, which is equal to M. I'm going to FOIL this in, so I get mg over M minus big M times T over M. This M cancels with that M. And so now I'm going to try to isolate for T. So I get them all to one side. So I'll add this T to the left side. I would add this to the right side. So I get T plus big M times T over M is equal to mg over M, not M. I'll just get mg plus mg mu K. And then I want to isolate for T, so I'm going to factor out this T. So 1 plus M over M is equal to mg plus mg mu K. Divide that over, so I'll just get mg plus mg mu K over 1 plus M over M. Answer right there, you can factor out an mg, it'd be the same thing. Alright, now for part G. Oops. Now it's asking you for the if you add friction, what happens to the tension in the string. So I'm always gonna set up the forces for the top block, which is just T minus Fk is equal to big M times A. But then I would add Fk over. So with the presence of friction now, the tension will increase. There you go. Part H asks for more free body diagrams. So I'm going to start off with the big M on the surface. So it's being pulled to the right by this tension T. It has an Fn component. It has an F of G that's equal to Fn. It has the force of friction on the table, which is less than T. But then it also has the force of the contact from the block right in front of it. I'm going to call it MM. So there's 5 forces in total. And then I'm going to do the other block that's on the table, which is small m. Has a force of Fn. Has F of G, which is equal to Fn. And then it also has Fk, friction from the table. And then it also is being pushed forward by the contact force between the big block and that. So this one only has 4 forces. And then now for the hanging block, which is M, it's being pulled down by Fg, and then the tension going up that counteracts that. Fg is greater than the tension, so the Fg vector is bigger. And that should be all the forces for these blocks. Alright, moving on to part I. it's asking us to find the acceleration of the system. So I want to set the net force for the whole system as a total. So this is f of g of the hanging block minus fk1 minus fk2, which is just the fk's of the two blocks that are sitting on the surface. And then this is the hanging block plus the smaller block plus the bigger block times the acceleration. Fg of the hanging block is just mg minus fn. I'm going to expand fk into fn mu k minus fn mu k. This is fn1, fn2, which is just 2m plus m times a. And now the mass of the smaller one is equal to 3g minus fn1. I'm going to say this is fn of the bigger blocks. This is mg mu k minus, this is a smaller block, so mg mu k. And then this is equal to just 2 times 3 plus 2 times a. And so this is just 3g minus 2g times 0.18 minus 3g times 0.18 is equal to 2 times 3 is 6 plus 2 is 8a. Now 3 times g is 29.4. 2 times g times 0.18 is 3.528. And then 3 times 9.8 times 0.18 is 5.292. All that divided by 8. Putting that all into your calculator. And you should get A is equal to 2.5725. But I'm going to say that's plus because the line of motion is moving down for the hanging block and moving to the right for the two blocks on the surface. So I'm going to say it's moving to the right and down. But that's the line of motion, so I'm going to say plus meters per second squared. Alright, going on to part J after this. Finding tension in the string. I'll set up the hanging block, that's the easier one. So Fg minus T equals Ma. F of G is just equal to Mg minus T equals Ma. I can isolate for T, which gives me T is equal to Mg minus Ma. Factoring out M, I get G minus A. So T is equal to 3 times 9.8 minus A from the last question was 2.5725. And so T, putting all this in your calculator, is 21.6825 newtons. But then it's pointing always towards the pulley. And that's the direction. And tension is a vector, so it needs magnitude and direction. There you go. Alright, moving on to part K now. It's asking for the contact force between the two blocks. I'm going to set up the net force for the small block that's on the surface. So Fm minus Fk is equal to Ma. So I'm solving for the contact force Fmm, so I'm going to isolate for that. Move mu k or Fk over. So I'll get Fm m is equal to 3 times acceleration was 2.5725. F of k is equal to Fn mu k. So Fm m is equal to 3 times 2.5725 plus F of n is equal to mg times 0.18. So F of m is equal to 3 times 2.5725 plus 3 times 9.8 times 0.18. And plugging all that into your calculator, F of m is equal to 13 newtons. Has to be positive though, or a plus sign, because force is a vector, and it's moving it forward to the right. So say positive because line of motion. All right. Going on to part L now, do it right here. So part L asks if the system has a res, what is the velocity, the final velocity after it travels 20. So I'll use common form. Okay, Vi is 0, so that cancels out. So I get Vf squared equals 2. Acceleration is 2.5725. And then the delta y, it changes, it goes down by 20. But since the line of motion goes downwards, I guess it moves positive 20. So VF equals radical 2 times 2 point. So plugging that into the calculator, your V should be 10.144 meters per second, positive as it goes in the line of motion. Alright, going to part M now. So I have to find the time. So I'll use delta y equals VIT plus 1 half AT squared. VI 0, so that cancels out. Delta y changes by 20. So 1 half. Acceleration is 2.5725 t squared. I multiply 2 to both sides. That's 40 divided by 2.5725 equals t squared. Take the radical of both sides. I get t is equal to 3.94 seconds. There you go. Alright, for this last part, is asked me to draw a bunch of graphs. So, first graph, I'm going to draw the, okay, let me just set this up real quick. So, I'm going to start off with the position versus time. So, y, and then this is t in seconds. And so, position versus time looks a little something like this. That's it. The next graph is going to be the velocity versus time graph. So I have this. This is t in seconds. This is v meters per second. And so the velocity graph is like this, straight line. I'm going to do the speed versus time graph now. So this is t in seconds. This is the absolute value of velocity in meters per second. And so it looks the exact same. There's no change. And then now acceleration versus time graph. This is t in seconds. This is a in meters per second squared. And so the graph is just straight across because we found earlier that our acceleration is a constant because it doesn't change. And so it's just always positive 2.5725. And then finally the force versus time graph. I'll try to draw it down here. Force versus time. So F. Similar to acceleration graph, it's just a straight constant horizontal line. That's it for this first FRQ. Thank you for watching, and see you in the next FRQs maybe.